1.33. Okay, 1.33 versus 1.34. Quadratic's a little better, but about 1.3% hydrolysis here. So that's one of the things that's new. In Chem 1A, you just learned that weak bases and weak acids partially hydrolyze. In Chem 1B, we're going to figure out the percent hydrolysis. Now, the stronger the acid, the greater the percent hydrolysis, and the stronger the base, the greater the percent hydrolysis. I mean both. And so here, ammonia is a weak base, only 1.3% hydrolysis. Water, do we do anything with water? No, we just ignore it. On exams, unfortunately, sometimes people, in the confusion of the test, try to put numbers in here. Screws everything up. So the ammonia comes out to 0.0013, no, 0.01. Is that right? Yeah, 0.00134. If you use the simplifying assumption, 0.00134. Did you guys test this? Check it? And it checks out? Comes out close. What did it come out to? 1.81? Okay, that's okay. All right, now what did you do? Did you go to step 2 or did you not go to step 2? In other words, this. If you look at this hydroxide, do you expect much additional hydroxide?
No. It's about 1.0.
Yeah, you don't expect much. How many people went to step 2, KW?
Just checked it.
You just checked it? And how much did you end up getting?
It came up like the same pH as the...
All right, well, let's go to step 2 then, because just don't take my word for it. You should take a look and see for yourself. So let's go to H2O plus H2O liquid and see how much additional hydroxide we're going to get from autoionization. So this is the end of the line for ammonium. This is the end of the line for ammonia. But wait a minute. There's something that's bugging me. You know what's bugging me? Ammonium and hydroxide, this reverse reaction has a driving force because we're going from a stronger acid, ammonium, to a weaker acid. What's the weaker acid? Water. And we're going from a stronger base, hydroxide, to a weaker base. What's the weaker base? Ammonia. So there's a big driving force for the reverse reaction. So shouldn't ammonium and hydroxide completely react and reset down to 0 again?
No, the dynamic is 0.
Yeah. And so because it's a dynamic equilibrium, there's always going to be that concentration because you cannot stop the reaction. You cannot stop the collisions, right? The collisions are always happening. So it'll replenish itself and it'll maintain this, right? But what we want to see is if we get some additional hydroxide to this. And so what we're going to do is we're going to bring this hydroxide up here, right? And so we're taking it from here. The ammonia and ammonium shouldn't change, and we're going to get 0.00134 molar hydroxide. How much initial hydronium do we have? 0. We're going to assume water's in nothing. And now we're going to let water collide and add some more. But isn't this 10 to the minus 7 molar? I already know how much water ionizes. So many people on tests write 10 to the minus 7 molar, 10 to the minus 7 molar here because when water autoionizes, it produces 10 to the minus 7 and 10 to the minus 7, doesn't it? So what would you say to that? You'd say, no, that's wrong, right? That's wrong. If X is not 10 to the minus 7 molar, why? Okay. One, this could be thought of as a Le Chadel's principle. We already have a lot of hydroxide. We aren't going to need more, much more. We need a little bit of hydronium. Or 2, if you don't like that predator and prey thing, why don't you come up with your own analogy? Or, why don't you come up with your own mental picture of this? This says the same thing. What is your mental picture of this? Why isn't this 10 to the minus 7 and 10 to the minus 7 molar? kW, this is what we get, right? And so somebody tell me why it isn't with their own. Or if you don't want to come up with your own, then repeat somebody else's. You know, but it's much better to come up with your own.
Is it just a lot of hydroxide that'll attack the hydronium to go back to water?
Yes. There's a lot more hydroxide around. And so that's going to keep the population of hydronium way down. So it can never build up to 10 to the minus 7 molar because the reverse reaction is going to be more favored. Well, anyway, just come up with some analogy that tells you this isn't. And so that analogy helps you understand when water is an important contributor and when it's not. Because the most would be if it was open field, you know, no predators around, open field, you're going to form 10 to the minus 7 molar. But when you have a lot of hydronium or hydroxide hiding in the grass or something, are you going to build up? No, you're not going to build up as much hydronium. So the maximum amount of hydronium you can get is 10 to the minus 7 or less. Will 10 to the minus 7 have an impact on this? No, because we got to move it. 1, 2, 3, 4, 5, 6, 7. The most we're going to add is out here. Is that going to make any impact on this? No. And in fact, it's probably less. So it's 8, maybe 9. Is that going to have any impact on this number? No. Therefore, we could skip this step. Right? But let's go ahead and do this step. Because, you know, you shouldn't always just take somebody's word for it because you don't know the basis of that rule. You know, is a rule the same thing as a law? Solubility rules. You know? Or the same thing as a theory? No, it's just a simple rule. And so you don't always take somebody's interpretation of that rule. And so let's go ahead and do this. What do you think about the simplifying assumption? I'll solve Kw down here. Kw is the hydronium total times the hydroxide total. And this is going to be x 0.00134 plus x. What do you think about the SA here? Pretty good? Yeah, it should be great because it's 1.0 times 10 to the minus 14, but let's go ahead and try it, even if we can't tell, because that means this calculation is going to be simple. X times 0.00134, which means that x is 7.5. Give me one more digit. 1 times 10 to the negative 12. Wow. And so here, is the SA valid? This is 10 to the minus 3 initial. So we got 10 to the minus 12 over 10 to the minus 3, which means it's going to be 10 to the minus 9 to 10 to the minus 7. It's a 10 to the minus 7% change. Was the SA valid? Yeah. I mean, 10 to the minus 7 is nothing. And so this is a really good. But we need to double check to see if the answer is correct. So 7.51 times 10 to the minus 12. The molarity of hydronium can only pop up a little bit before being taken out by hydroxide. Just a little bit. Nowhere near 10 to the minus 7 molar. And then over here, this is equal to 0.00134 plus, how many zeros do I need? I need 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11 zeros and then a 751. Which is going to give me 0, 0, 1, 3, sub 4. And then after 4, I need 1, 2, 3, 4, 5, 6 zeros. 1, 2, 3, 4, 5, 6 zeros. 7, 5, 1. Was that a significant contribution? No, totally insignificant. And so, speed is key sometimes, and, when we can skip a step, that saves us a lot of time to work on other problems, right? And so, but we should double check this. Does this number double check? Does it equal 1 times 10 minus 14? Yeah? 1.006 times 10 minus 14. That's good. 1.006 times 10 minus 14, which checks. It's just a rough double check. All right, so that's good. So it depends on what the question is. Would I do step 2? Well, it depends on the question. If I was asking just for X in step 1, no, obviously. But if this were an open-ended question, I would have to do step 2. Why? If this were an open-ended question, I would have to do step 2 because, well, you go, wow, that's ridiculous because, did it really change? Am I really going to write this as my answer? The whole thing? No. And so, yes, it is. It's not even worth doing for hydroxide because it's so negligible. But if this were an open-ended question, you'd have to do step 2 because why? Even though step 2 contributes a totally negligible amount of hydroxide, it contributes a significant amount of hydronium. We need to do step 2 to figure out how much hydronium was generated in this reaction, right? Because we started off with nothing, and there's actually, can you believe it? There's actually hydronium in a base, a weak base solution. Where does that hydronium come from? Water. And so how do we define what a basic solution is? A base has a greater concentration of hydroxide than hydronium. Acids have a greater concentration of hydronium than hydroxide, but all solutions have both hydronium and hydroxide. And so what we do is to understand the inventory of the solution. The inventory is what species we're going to find in solution. What is the number 1 species we're going to find in solution? Ammonia molecules. What's number 2? Hydroxide. What's number 3? No. Ammonium. So ammonia is 1, hydroxide is 2, ammonium is 3, and hydronium is water is number 1. Well, water is a solvent. Water is always number 1, so we'll just skip it. And so this is what we do. Okay, when I have a solution that's labeled 0.100 molar ammonia, that's its ideal. That's what we think when we make this. But in reality, in this solution, we're going to have an ammonia concentration that is equal to 0.09866. We'll just go 0.0986 molar. And the next most abundant would be hydroxide. Hydroxide has a concentration of 0.0134, just slightly above that. And then the next one would be ammonium. Ammonium is going to be 0.0134. So are these two concentrations equal, hydroxide and ammonium? No. Hydroxide is actually a little more, but you can't tell. And then, wait a minute, isn't hydroxide, wait, I got 0.0134 from step 1. shouldn't I add 0.001340000 to O to that? Didn't my hydroxide double? You know what a lot of people do? They add both. They add the hydroxide from step 1 here to the hydroxide from step 2 here. They just add them both, so double it. What was the problem with that? If somebody did that, your friend, what would you tell them their mistake was?
Still count step 2 to do second.
Yeah, you're double counting. You already took it into account because we transferred all the hydroxide from step 1 to step 2. That happens about every semester. That happens about to 1 or 2 students. They'll double it. They just keep adding it. And then finally, the hydronium is equal to 7.51 times 10 to the minus 12 molar. This is what we call the inventory of the solution. So oftentimes I'll ask you, what the inventory of the solution is. If I just ask you what the pH is, do you need to do step 2? Not really, because what you could do is you could get the pOH from step 1 and then calculate the pH based on that. You don't really need to do step 2, and that saves you time. And so if I ask you just what the pH is, then it's easy. You could get the pH directly from the hydronium in step 2, but the quickest would be to get the pOH and then convert that into a pH. And the pH comes out to 11.1. Is that what you guys got? All right. How late do we go today? 55. Okay, that leaves 10 minutes for you to do this problem for me. Do this on 1.0 times 10 to the minus 6 molar ammonia. Actually, let me do it like this. Sorry, let me change this. We're going to do 1.0 times 10 to the minus 8 molar ammonia. 1.0 times 10 to the minus 8 molar ammonia. Are you going to worry about? Okay, then let me change it to this. 1.0 times 10 to the minus 6, sorry, molar. Are you going to worry about it?
Yes.
Well, we'll try it and see. So try to do this with a little bit of speed and try to finish this 10 minutes.
What do you want to play?
Everything. KV is 1.8 times 10 to the minus 5. Why don't they have a KV table? When I look at there's only a KA table. There's a reason for that. I'll tell you next time. minus 5. Yeah, KB is 1.8 times 10 to the minus 5.